Well, welcome to our review video on volume. We're going to cover a couple things. We're going to talk about volumes by discs, volumes by washer, and then we'll even get into some of the known cross-sections, hence your slice analysis. All right, so let me just start off with a few pictures of what we're talking about. In this case, you have this graph y equals radical x, and we've got our x-axis there. We're going to revolve it around this line. Now you'll notice when you draw your slice in, there is this nice gap between your slice and this axis of rotation. And what that is creating, if you can picture this coming out at you in a round, it's creating this 3D shape that you're seeing here. And because there's a gap, it's creating this really neat hole in the middle of this. Okay, so I tried to cut that in half for you and get a picture. And like I said, you're creating this hole all the way through your figure. All right, and we're creating this washer or a donut, so to speak. Okay, now you can clearly see, I think, that you have two radii. You have from this outside edge to the centerpiece, and then you have this little edge to the centerpiece. So that's why we have, I'm going to call that big R, and we have little r. Okay, so we've got our big R and our little r. And we know our formula, hopefully you can recall, is pi big R squared minus little r squared when we have a washer, because we have two radii. The radii of this large circle and the radii of this little circle. All right, let's take a quick look at the slice analysis section. So I've pulled out a few pictures here so you can kind of get a better visual of what they look like. And basically, it looks like on this first one here, our base is almost a triangular shape, and our slice is a semicircle. And we're just really putting this diameter of the semicircle across the picture, and you can see the neat shape that we're creating out of this nice three-dimensional shape. In this example here, my base just happens to be rectangular. And we've got nice equilateral triangles. And again, it's making this very interesting three-dimensional, almost spiny-like shape. In this case, my base looks like it's a circle, maybe x squared plus y squared equals 2. And I've got a nice isosceles right triangle, and you'll notice the base now is a hypotenuse. Okay? Now, what do we need to see from you? Well, we really need to see a perfect setup of your slice analysis. All right, and what are we looking for exactly? Well, let's talk about our shapes. If they mention the word square, okay, you're simply going to draw yourself a square and ask yourself what is the relation between the base and the height. All right, and here's your slice analysis. BHAV, okay, BHAV, whatever you want to use, BHAV, the base, all right, is your f of x minus g of x, or whatever your two functions are. Okay, if it's a square, look at the tick marks you just made. We just said the base and the height are equal, so you repeat that. Yes, you write it down twice. Area, you're going to do two things. You're going to write your area formula. Area equals base times height. Now apply whatever your base and height are. So now I can say that's f of x minus g of x squared. And volume, remember, is simply the integral of whatever you wrote for your area. Okay, if you do not have a pi in it, then you don't put pi in this section. It is simply the integral of your area. Okay, now square is obviously a very simple one. Let's kind of run through a semicircle. Okay, and there's nothing to memorize, guys. It's simply sketch it out. Okay, so if here's my cross section and I were to put a semicircle in perpendicular to the base, okay, this time, this distance here of your semicircle represents its diameter. Semicircles don't have bases in height, so this one starts with a D for diameter. And again, that's your f of x minus g of x. Okay, then you need the radius of the circle. So that's 1/2 f of x minus g of x. Notice it's half of that quantity. Okay, then you need your area. And again, start with the formula. It's a semicircle. 1/2 pi r squared. Now plug your information in. 1/2 pi, take whatever you have written for radius and square it. 1/2 f of x minus g of x, that quantity squared. Okay, now here's where the volume comes in. And again, you don't have to memorize this. You can write this two ways. You can simply say it's 1/2 pi, the integral from a to b, of 1/2 of f of x minus g of x squared. Or you could actually go further and do the math. If you square a half, you get a fourth, and a fourth times a half is an eighth. And that's where the 1/8 comes from. But you don't actually need it out there. Okay? Slow down and just write your steps out. Hence the word analysis. You are analyzing the slice. Okay? The other two that you need to be, or three I guess you should be aware of, is the triangles. If they say isosceles right with the leg on the base, draw it on your paper. You can't screw this up. Here's the base. Leg is on the base. The base then and the height are equal. Okay, so you go base, height, they are equal. Area is 1/2 the base times height. Plug it in the formula, 1/2 that quantity squared. Volume is simply its integral. If they say isosceles right, hypotenuse on the base. Okay, draw it out. Those are the equal sides, the hypotenuse is on the base. Now what you can't see in there is the height. Okay, the height is perpendicular. You're going to have to draw it in yourself. Okay, so now compare your base to your height. This is your base, and your height is how much of it. Okay, well, we've worked it out in previous videos. Your height is half the base. So I'm starting with that b half, base, f of x minus g of x. Height, look at your picture. It's half f of x minus g of x. Okay. Now your area, start with the formula, 1/2 base times height. Now just simply plug them in. It's 1/2 the base times the height. So that's 1/2 the quantity f of x minus g of x squared. That's simple. Whoops, I put my square there. All right, just follow the steps. So this time your volume would have a 1/4 in front. Probably the ugliest one to remember is the equilateral triangle. Okay, equilateral triangle meaning all sides are equal and all angles are equal. They're all 60 degrees. In this case, let's say your base is f of x minus g of x. You need to recall that your height is radical 3/2 times the base. So times my f of x minus g of x. Okay, and again, maybe the 60 will trip your trigger. The sign of 60 is radical 3/2. Maybe that'll help you memorize it. But then it's the same. BHA. Area equals 1/2 base times height. Plug it in your formula. 1/2 radical 3/2 times the f of x minus g of x squared. That's where your radical 3/4 comes from when you integrate that. So our first question to tackle tonight is a non-calculator question. All right, so let's go ahead and sketch this puppy out. We've got y equals 3 radical x. Now we all know what radical x looks like, and 3 is just going to stretch that graph up a little higher. So we've got 3 radical x. I'm going to use a different color here for y equals 6. And x equals 0. All right, and lastly, I'm just going to go through and I'm going to label my intersection points. This would be the point 0, 0. This here would be the point 0, 6. And of course, I need to figure out what this intersection point would be. Now, how do you do that without a calculator, you may be asking? Well, you just simply set those two equations equal to each other. So I'm going to say 6 equals 3 radical x. My goal is to get x by itself, so 2 equals radical x, square both sides, and hopefully you've got x equals 4. So that corresponds to that point right there. So I'm going to say the coordinates there are 4, 6. All right, now let's assume we're talking about the region that is in between those 3 curves that they've labeled for us. So before we get started and, attack a question, I just want to be clear on, how we would set this up. If we're integrating with respect to x, okay, that means if I have x's in here, my bounds, that means my line would be a vertical slice, and my bounds would move left to right here. This line can move left and right. It would move as far left as 0 and as far right as 4. So if I'm with respect to x, I'm going from 0 to 4. Or if I'm with respect to y, if I have whatever dy in here, that means my slice is horizontal. And in this case, this line can only move up and down if it's a horizontal slice. It can move down to 0 or up until a height of 6. So those bounds would be different. All right, so let's attack our first question here. Let's go ahead and revolve this for part A. Let's revolve this around the line y equals 6. All right, now let's go back up to our picture. Y equals 6 happens to be this line that we already have there. Now you'll notice my slice is right on this line. Is there ever a gap between my slice and this line y equals 6? Is there any empty space there? No, and hopefully that's pretty clear. So this time we have a disk. So let's just verify we have a disk. And our formula for disk, or our volume for a disk, is simply just pi r squared. We simply have one radius to square because there is no gap. The other thing I want to really stress in our notebook here again is if our slice is vertical, we are strictly saying upper minus lower, upper minus lower. So as I look at this picture, I would say my upper is 6, my lower is 3 radical x, and this slice can move left and right, so from 0 to 4. All right, now of course this has been a non-calculator question in our recent exams, and like we said at the top here, non-calculator. Your gut's gotta tell you, when you see a quantity squared, all right, we all passed algebra, when we see a quantity squared, that simply means to write it twice and FOIL. Okay, we don't just square two terms, make sure you write it twice and FOIL. So I've got pi from 0 to 4, that's 36 minus 18 radical x minus 18 radical x plus 3 times 3 is 9. Radical x times radical x is simply just x. All right, and of course I'm going to clean that up before I go any further. 36 minus 18 radical x and 18 radical x makes 36 radical x plus 9x dx. Okay, at that point, we've done the hard part. Now we just simply integrate, plug our bounds in, and I'm going to leave it at that, and I'll let you play with that on your own there. So again, we would integrate, plug our bounds in. For part B here, we want to do something very similar. Let's say we want to revolve that region around the line y equals 10. So we're going to do something very similar. Let's go back and take a look at that picture. That was the line y equals 6, and I'm going to use red, and I'm going to draw in a new line, and I'm going to call that y equals 10. Okay, now you'll notice there is a significant gap between my axis of rotation and this slice. The second there is any tiny little gap, we now have a washer instead of a disk. Okay, now how do we solve a washer problem? Well, we're going to stick 2 endpoints on our slice. We're going to go from the axis of rotation to the bottom dot there for our big R. From the axis of rotation to our top dot there is our little r. Now we simply just need to put it all together. So I'm going to describe that big R. And again, because this is a washer, I've got pi big R squared minus little r squared. So I've got pi, the integral from 0 to 4. My upper is 10 minus 3 radical x, that quantity squared, minus 10 minus 6 squared dx. Okay, and again, I'm going to leave it at that part, and we can figure it out on our own there, but again, you would have to FOIL this term out, FOIL that term out. Part C, region R is the base of a solid. For each y, where 0 is less than or equal to y is less than or equal to 6, the cross-section of the solid is perpendicular to the y-axis is a rectangle, whose height is 3 times the length of the base. Write but do not evaluate an integral expression that gives us the volume of the solid. All right, well, several things to catch. First of all, the most important is you are perpendicular to the y-axis. So if we take a look at that picture, we are now doing a horizontal slice. That's what had to come into my head. I am perpendicular to the y-axis. Also, there you start talking about a rectangle. So this is a slice analysis. We need to see a full-blown out slice analysis. Okay. So the first thing I'm going to start with is instead of saying upper minus lower, I'm saying right minus left. I am basically picturing a rectangle popping out at me. So the base is now right minus left, and I need to put everybody in terms of y. So if you recall, this was y equals 3 radical x. I'm going to say this is y over 3 equals radical x, or y squared over 9 is equal to x. All right, so my base is y squared over 9. Technically, mine is 0. I'll write it, but we obviously don't need to say that. And now they describe the height. The height is h equals 3 times the length of the base. So 3y squared over 9. Okay, now start with your area formula. Write the formula first. Area equals base times height. So my formula is y squared over 9 times 3y squared over 9. And if I clean that up, I'm going to say my volume equals, notice there's no pi in my area formula, so no pi in my answer. The integral of 3y to the 4th over 81 dy. And this time, just watch those bounds again. We are moving not left and right, but up and down, so from 0 to 6. And we simply had to write, but not evaluate. Our second problem for the night is calculator active. Now, I'm sure we can all draw this without a calculator, nothing very mind-blowing, but since they let us use a calculator, let's go for it. So grab your calculator, get this typed in neatly, and let's focus on a real nice window. So you can see I've got my equations in there, and of course I found that point of intersection right off the bat. Now, what do we want to show the grader on our AP exam? Well, we want them to know we know how to get that intersection point. And of course, we're just going to set those two functions equal, and we are going to write that down and show the grader we know what we're doing. And now you are welcome to call that point AB, and again, this is fine on our AP exam. Let's just show the grader what we're doing. And I'm going to say this is equivalent to 4.497, 1.503. Okay, obviously this is what I'm storing into my calculator for A. This is what I'm storing into my calculator for B. So our first question here is, let's go ahead and get the area of this function. All right, now, you might be thinking, all right, it's always easy if I go vertical. Well, let me draw one vertical line in here and just ask you, does this vertical line, will that vertical line take us all the way through this shaded section or this region here? Okay, is this function always on top? Is this function always on the bottom? And the answer, of course, is no, because if you look right here, I now have a different function on top, although the same function on the bottom. So if you're going to find the area that way, you would have to do two separate areas. Now, what might be easier, whether you like it or not, it's actually easier if we put this as a horizontal line, because now we only need one area, or one integral to represent our area. So let's go ahead and practice writing it in terms of y. So let's just first start with those bounds. I'm going to integrate from, let's see, this line can move up and down. So I'm going to say that's from 0 to this height that it reaches, of course, is what we stored into alpha b. Okay, 0 to b. Now again, I'm saying right minus left, but if I'm in terms of y, I cannot use the ln of x and 6 minus x. So I'm going to quickly solve those equations. Basically, to get rid of an ln, I'm going to zap both sides, so I'm going to exponentiate. So this function here is now e to the y, and this linear function, I'm basically just going to solve for x. I'm going to add the x over here and subtract the y over there, so I get 6 minus y. So when I go ahead and integrate this, I am going to say the right minus left. So 6 minus y minus e to the y dy. And, you know, it's a little easier, it's a little quicker than writing two separate integrals. So part B here. It says the horizontal line y equals k divides region R into two regions of equal area. Write, but do not solve an equation involving one or more integrals whose solution gives the value of k. Okay, so basically that line has to be horizontal. Now, it's probably almost near where my red line is, except it looks like maybe there's more area up there than down there. So I'm going to go ahead and draw a new line, and maybe it's right about there. Anyways, this is the line y equals k, and the region above it and the region below it have to have two equal areas. So I think I can do this in one integral since I went horizontal my first time. I could say that this area down here, okay, so basically the area from the lowest value is 0 to the highest value of k. So my integral would go from 0 to k of right minus left. So let me get that started here. I would say the integral from 0 to k and my right minus left, so my 6 minus y minus e to the y dy, has to equal basically how much of the whole area. Well, I didn't evaluate this area. Let's just go back and call it c. If the whole area is c, and I'm splitting this into two equal areas, then I would say this would have to equal half of c, whatever that number happened to be. Obviously, we did not evaluate it on our calculator. Now, that's not the only option. I think you could do it another way. You could almost write two integrals. Notice it said involving one or more integrals. You could say the area from 0 to k is equivalent from the area from k to b. Would you agree with that? This area has to equal that area. So let's go ahead and say, or you could write it in two separate integrals. We could say 0 to k of 6 minus y minus e to the y dy has to equal the integral from k to b. And of course it would be the same thing, my 6 minus y minus e to the y dy. Now you might be thinking, why are we talking about area so much? That was kind of last night's idea. This is volume, so let's go ahead and throw one last volume piece in there. Let's say we now want to revolve that area around the line x equals 8. Okay, so again, that was at 6, 8 would be right about here, x equals 8. So I need to be perpendicular to that axis of rotation, so I do have to use a horizontal slice. It's not an option. You need to be perpendicular to that axis. So you'll notice that there is a gap here between the end of my blue dots here and my axis of rotation, so I have a washer. And let's go ahead and set it up. Now just remember, you are saying right minus left, so I'm going to go ahead and draw these brackets in. From one end to the axis of rotation is my big R. From one end to the axis of rotation is my little r. So I'm going to say volume equals pi. Notice this line's moving up and down, so it's still from 0 to b. My big R, my right minus left, is going to be 8 minus e to the y squared minus my little r is going to be 8 minus the quantity 6 minus y squared dy. All right, and again, we're just going to set up, not evaluate. We could use our calculator, but we'll call it good from there. Well, so that's going to do it for us. Hopefully we've got a nice review of area and volume the past 2 days, and we'll look forward to some great practice tomorrow.